Hello, my name is Tugtekin. In this video, I will present our paper on language model adaptation. This is joint work together with Dietrich Klakow, Emmanuel, Vincent, and Denis Jouvet. Also, this work was supported by the European Union's Horizon 2020 Research and Innovation Program under the project name Comprise. In recent years, personal assistants play an important role with smart devices and mobile applications. The collected data are then used to train large language models. In these models, each spoken message reveals personal information. Therefore, removing private or sensitive information from the input sentences is necessary. With the growing public interest in privacy, this issue became an hot topic, and some European Union's GDPR rules also regulate storing the private data. It is obvious that the user data might contain critical information such as passwords, credit card numbers, or even health status. Therefore, spoken messages which contain sensitive information about the user characteristics should not be centralized in a single place. But unfortunately, hiding this private information leads to less accurate speech cognition systems because the word distribution in the privacy transformed data does not match that original untransformed text. So class-based language models have proved their success in training with small datasets for fast model adaptation. By grouping words with similar distributional behavior into equivalent classes, these class-based models have fewer parameters to train and can make predictions based on longer histories. In our approach, we mainly use the class-based idea for our problem formulation. To do that, we propose a method on how to recover the performance loss when training on privacy removed data. We employ a mixture of neural and word-based language models alongside class-based models, where each named entity category corresponds to one class. By doing so, entities were hidden using by word replacement over some random name entities from the same entity class. Our methodology consists of a two-stage adaptation scheme. After getting sanitized data, the first part here performs generic language model training with several models. Then the next stage here performs an adaptation using a small amount of original data, in other words, untransformed data. Here the block diagram provides a general overview of our proposed adaptation approach. We consider sanitization of text data annotated with 4 labels: persons, organizations, locations, and miscellaneous entities such as date or time. The sanitization is performed using the word-by-word same type transformation strategy. With this approach, even when the entity recognizer is failed to detect word occurrence, an attacker cannot easily distinguish whether these words are the results of an actual transformation or not. Given this sanitized input text, the class-related probabilities can be estimated by the maximum likelihood principle, which simply counts the number of occurrences of the words divided by the total number of word occurrences in that class. We incorporate class-based models with sanitized word-to-class mapping into the finite state transducer framework. And after training the individual models at stage A, here depicted on the left, we apply 2 different strategies in the next stage. For word and class-based models, we focus on using Unigram language models to adapt trigrams. This approach combines unigram and trigram information following the fast marginal adaptation idea. As an initial distribution, it uses the trigram trained on the background corpus, and the desired trigram has to satisfy that its marginal is the unigram trained on the adaptation data. So in summary, the final model is scaled up or down depending on whether it is more or less frequent in the adaptation data than in the background text. For the neural language models, we adopt a fine-tuning idea where we first train a background language model on the entire sanitized training set. Then the adaptation is performed by fine-tuning the final softmax layer. The decoding can be easily done for n-gram originated word or class-based language models because of their ARPA style format. However, to use neural language models into the single pass decoding, we also evaluate an n-gram approximation of neural models to avoid some decoding delays. Finally, we produce an n-gram ARPA language model, which is later used in the single pass decoding. We evaluate our adaptation schemes using the AMI corpus, which is containing multi-hour meeting recordings. Following the official AMI partition, we ensure that no speaker appears in more than one set. Here you see some statistics on the left side from the corpus where the overall duration is 100 hours. For the name entities, we use annotated text given by AMI named entity instructions to identify entities in the sanitized data. We use a pre-trained entity recognizer by spaCy models. As an acoustic modeling, we use Caldi's chain system based on the time delay neural network architecture. During the experimental evaluations, we use word error rate and perplexity as objective metrics. We first compare the generic language models trained at the first stage without any adaptation or interpolation methods. These individual models are given on the left here. On the right, the results table firstly presents the performance obtained over the sanitized input text. On the middle side here, we can see some language model results trained on the original untransformed data. And finally, we see the results on the right when adapting the models with an untransformed adaptation set, which is around 12% of the training data. For the sanitized data, the best results are obtained using either the class-based M2 models in the first pass decoding or through some rescoring with the LSTM in M4 model 4. The best results are obtained when an LSTM language model trained over original data used in a second pass lattice rescoring, but this increases the computational requirements and also adding some delay before the output. Using limited amount of the untransformed data, here we observe the benefit of adapting language models initially trained on a large set of sanitized data. Both word error rate and perplexity results improves for each model type. This slide presents interpolation experiments. We employ a linear interpolation of the previously adapted models with the best weight combinations. On the first line, you can see the combination of word and class-based models. Then it is possible to observe the effect of adding LSTM-based neural model. We can conclude that here we obtain the best results with the interpolation of LSTM language model at the final stage. Yeah, to sum up, this paper proposes language model adaptation schemes over the privacy transformed text for an ASR automatic speech recognition task. The privacy removed text is obtained by applying data sanitization techniques using the named entities. This relies on recognizing and replacing entities with other words from the same class. However, this may harm language model training because of the train test mismatch. So this paper aims to fill this gap by focusing on the adaptation of language models initially trained on privacy transformed sentences. To do so, we combine class-based language models and neural language models, and our experimental analysis show that the training a language model on privacy transformed data results in almost 11% relative word error rate increase compared to the training and original training on the original untransformed data. After the adaptation using a limited amount of original untransformed data, we can achieve 8% improvement over the model trained only on privacy transformed data. As a future direction, we can use these ideas in an extended framework, maybe to a more challenging text with a large set of entity modeling. One can evaluate this adaptation strategy to hide other private information like gender, other topics that span diverse domains such as finance, healthcare, or politics. Anyway, let me stop here. This is the end of my presentation. Thank you for listening to me.